biodegradable material, because PLA is also biodegradable material, yeah, from this point of view. But the Harshit's presentation, it's, let's say, useful for me, yeah. We didn't talk before, yeah, and I have, let's say, some information about the most used methodology, technology for 3D printing. But of course, I will skip the information that we already presented, because you already presented very well, let's say, how it's working, yeah, each 3D printing technology. And I will focus more, let's say, on advantage, disadvantage, yeah, of the method, to highlight a little bit the accuracy, yeah, of each method, and so on, yeah. Hopefully, we will not be boring up to the experimental results. I'd like also to mention one problem more. I didn't count the minutes of my presentation, I mean of each presentation, and maybe I will not focus exactly, yeah, on the schedule that was already fixed for our presentation, for my presentation. I mean 1 hour and 30 minutes, because I fixed only the main idea, yeah, that I wanted to say, yeah, to share with you. Okay, so the evening lecture will be focused on 3D printing of biodegradable material. As you can see over there, we will talk about the PLA. Already talk PLA, but Harshit already talks about PLA, but will present, let's say, more results from this point of view. The impact PLA gray and high density PLA gray. I think also for you it's important to carry on the research with the others, let's say, PLA types. Another part is Extrudr BDP, yeah, including the Extrudr BDP Flax, Pearl, and Green Tech. The second, let's say, category of the biodegradable material that we used, fiberwood, Biofila linen, and Biofila silk. And of course, our goals were to compare, let's say, the already known biodegradable material with our material, and using a simple and interesting, let's say, extruder, we made the filament. We got the filaments from the granules, yeah, of course not on the production, let's say, lines, and we use it for the 3D printing in order to compare with Arboblend, Arbofill, and Arboblend reinforced with Extrudr BDP Pearl. So, additive manufacturing technologies. I think it's very nice and, let's say, complete, yeah, imaging of additive manufacturing technology, because you can see here VAT, photopolymerization, cured with laser, cured with projector, cured with lead and oxygen, and afterwards material extrusion. Here we can find the FDM process. You can see material jetting with cured with UV light, cured with heat, and milled to form. And you can see here, yeah, which are the let's say, main technology for additive manufacturing. And on the line, on the black line, you can see the producer, yeah, and of course Kalpak knows very well, I think, yeah, the producer, because he's on field, yeah, of 3D printing. Another one, binder jetting, joined with bonding agent, yeah, binder, you can see, yeah, powder bed fusion with the fused with agent and energy, fused with laser. We have here SLS and SLM technology, fused with electron beam. We have here ABM, okay, technology, and direct energy deposition, fused with laser and fused with electron beam. And the last one, sheet lamination, you can find over there, as already Harshit present, LOM, yeah, 3D printing technology. I think we created a good image from this point of view concerning the additive manufacturing technology. As I mentioned before, I put also the same, let's say, mostly used 3D printing technologies, yeah, nowadays. So, Harshit, we didn't talk each other beforehand, Yeah, but Harshit make the good presentation how is working each. Okay, please let me share with you some, let's say, strengths or weaknesses of each technology, because the others, let's say, physico-chemical processes, already Harshit mentioned. Also, already Harshit mentioned the application, but let's say it's important to know also the precision, the accuracy, yeah, of each 3D printing technology. So SLA technology, as you can see here, plus means strength, advantage, and minus, okay, means the weakness of the technology. So the first one, high quality surface finish. It's quite important, yeah, to have the high quality of the surface, yeah. But it's not up only by the technology. It's up also it's in the connection with the used material. Okay, we will see later. High accuracy, transparent, flexible material, fine features, details, market leader, large part size, important, large part size, wide product. But in the same time, you can see we have a little bit weaknesses. I mean, brittle, not suitable for mechanical parts, and post-processing because of the messy liquids used inside of the technologies. The next one, SLS technologies. Take into account the physical chemical processes fused with laser sintering process. High precision, the same. Functional parts, good mechanical properties, complex geometry, so we can obtain, yeah, complex parts using this SLS technology. Market leader, large part size, but in the same time, longer time, yeah, for obtain the product. Higher cost compared with FDM, because FDM, Harshit already mentioned, is the most used technology, and it's better, yeah, to compare from time to time with FDM technology. And size and weight. If you want to see the accuracy, yeah, better in this case, yeah, 0.3 compared with the first one, 0.5. SLM fused with laser. From the advantage, strongest functional part, complex geometry, but small building sizes, highest price point of all technologies. Yeah, compared with the other technologies, the SLM has, you know, the highest price. And but opposite, you can see a big advantage concerning the accuracy, plus minus 0.1 millimeters. FDM technologies. Of course, one of the most used 3D printing technology, rapid prototyping, low cost functional parts, limited dimensional accuracy for small parts, print layers likely visible on the surface, low printing speed. But take into account the accuracy, yeah, is the same with SLA technology, 0.5 millimeters. Material jetting, you can see over there concerning the physical processes, cured with UV light, and the advantage high temperature we can use, best quality surface finishing. Also high accuracy, transparent, color printing, and multi-material available during this technology. Brittle, and from this point of view, it's not suitable for mechanical parts, and high cost compared with the other technologies. Accuracy, it's quite good, 0.1 millimeters. Binder jetting, join, of course, with bonding agent. We have a low cost for this technology. We have large possibility to have large build volumes, functional metal parts, quality surface finish, high precision, but in the same time, look here, mechanical property not as good as metal powder bed fusion, speed limited, and there is a possibility to obtain the small part. Concerning the accuracy, you can see over there 0.2 millimeters in case of metal and 0.3 millimeters in case of sand. Lens fused with electron beam. You can see over there build fully dense shapes used in part reconditioning, yeah, these technologies. desirable metallurgy properties, but lack of different material for support structure and post-print machining as, let's say, a main disadvantage of this technology. The accuracy is the highest one, yeah, plus minus 0.02 millimeters. And the LOM 3D printing technology, this technology allows to obtain the large part size, good for large casting, very inexpensive material because, of course, we use paper, fast and accurate, good handling strength, environment friendly. Look here, very good, let's say, advantage, take into account the environment, because always we have to take into account the environment, yeah, especially for the next, let's say, year. Not health treating, but in the same time, you can see over there, part stability, smoke, surface finishing, dimensional accuracy, very difficult in producing hollow parts, yeah, with the hole, yeah, inside. It's very difficult. It's not suitable as a technology. And of course, this technology needs post-processing operation. Concerning the accuracy, you can see 0.2 millimeters in case of composite and 0.4 millimeters in case of paper. Let's have a look now about FDM technology. I mean the main advantage and disadvantage, and afterwards to see which are the main steps, yeah, for the 3D printing technology. I'd like to mention a little bit, yeah, some advantage. Does not use toxic materials, yeah, for FDM technology. It's important because we can use the equipment inside of our labs, yeah, inside of our office to work with it. Simple post-processing operation, because it takes only a few minutes, yeah, for the post-processing operation. Some 3D printers that I use FDM technology are very cheap, yeah, and you already know, yeah. Our students, you know, as a diploma, let's say, some possibility to build alone, yeah, one 3D printer. Friendly, silent, and secure technology, yeah, from this point of view. Use a fairly wide range of material, a simple production technology, whole parts, yeah. This time we can obtain the hollow part, yeah. It's not difficult to obtain this part. And compared to the other processes are using powder or liquid material, the filament is cleaner and easier to change, yeah. We already know the diameter in case of FDM technology. Of course, we know the diameter must be uniformly and so on. But take into account the producers, yeah, it's not a problem. It's a problem when we try to get the filament from the granules, because it's up to the range temperature. In our extruder, we fix the temperature between zone 1 and 2 with 5 Celsius degree, and I saw that also hard sheet use 5 degrees Celsius between zone, yeah, on extruder. And some disadvantage, the parts are not resistant in the vertical direction, yeah. I saw many researches when the, you know, sample put on plan, you will see also our research on edge, okay, on the vertical position. But on the vertical position, as my opinion, the results are not good. The precision, the accuracy of the part, it's up to the thickness of the filament, also is the disadvantage. Lower waterproofness, yeah, is also another disadvantage. And low resolution, the accuracy for small parts and, let's say, fine details on the micron level. Let's have now a little bit about the steps of the 3D printing technology. At the very beginning, we need the technical specifications. Yeah? We need the requirements. And afterwards, we can create the CAD design. Yeah? We can go to the optimized model using the finite element analysis. Yeah? Because always today, my colleague is, let's say, an expert in simulation and finite element simulation, and it's better to use not only in 3D printing, yeah, on the other application, yeah, to compare the simulation results with the experimental results that we got afterwards. Yeah, it's quite important. Afterwards, we obtain the optimized model. Of course, we can get the STL file. Yeah. After the STL file, slicer, we get the G code, and afterwards, yes, the material it's prepared for 3D printing. So this second phase we call, of course, manufacturing, and the first one we call design. Okay. After manufacturing, we go to the testing, because after manufacturing, we'll get the 3D object. Of course, we have to test it, yeah, and to have the final conclusion, passes or not passes, okay, the final product. Our experimental research, as I mentioned on the outline, I mean on the first slide, will focus, as you can see over there, on PLA, so the PLA material, let's say, group, and Extrudr biodegradable group, fiber wood separate one, and 2 types of biofila. I'd like to mention at the very beginning that the fiber wood is the best, let's say, biodegradable material, and we can get the best surface quality from this point of view. Yeah, it's unexpected. It's amazing, the quality surface. Harshit, try to use fiber wood. It's not expensive one. Did you use so far? No. Try to use fiber wood. It's very, very good and let's say easy to print, more or less like PLA. Yeah, material. In case of our material, as I mentioned, the producer, please, Harshit.
Recently, one of my colleagues who is working on renewable materials. So he has come up with the chopped fiber powder.
Okay.
That he has got from water hyson as well as from coconut.
Coconut, yeah.
So we are going to mix it with PLA granules and try to see if that can be converted into a filament. So that is the first thing which we are going to do in maybe early August.
Yeah, very good. Yeah.
We will move into that time.
Yeah, okay. So in case of our material, I mean Arboblend and Arbofill, the producer, yeah, other words, there are not filaments. There are only granules. So that's why we bought Extrudr. We got the filaments, not on the production line, as I mentioned, only for 3D printing. And you can see here inside of the our Extrudr, you use between first zone and second zone, yeah, 5 Celsius degree, yeah, between zone. And the quality, you can see afterwards some SM imaging, and you can see over there, yeah, the diameter, very good, 1.74 millimeters, but in case of Arbofill material, the shape, the, let's say, outline, outer diameter shape was not good from this point of view. So we started, but the results, of course, were we expected, yeah, from this point of view. We started for PLA, yeah, with different, let's say, infill, 50%, and you can see the tensile around 25. In case of 70 infill, you can see 30% for tensile, megapascal, and in case of 100%, we'll find around 40 megapascal. But we did, I forgot, I think we did a triangular pattern. Triangular. Hexagonal. So the infill partner was hexagonal one, yeah, in this case. But my colleague now tried to find, you know, an optimized infill partner, yeah, patterns in order to get more results concerning the tensile strengths, yeah. I mean not to use the regular one that are inside of the machines, okay, to create another one and to try, you know, to see what happened with new infill pattern in order to increase the tensile. Because as you already know, doesn't matter we are talking about the metal, we are talking about the polymers, the first research that it's compulsory to be done is the tensile strength. Okay? All my PhD students, always we started with this one. I choose for my experimental plan, let's say, the best results, the line with the best results for tensile strength, and afterwards with those samples, we carry on, yeah, all the research, let's say thermal, structural, and so on. Okay? Because this is the main step, yeah, in the research. And of course, you can see over there, of course, some position, yeah, for the sample. And input parameters, layer thickness, 0.1, 0.2. I saw that Harshit didn't take the layers parameters. Yeah, I mean layer thickness. I mean, you, yeah? Okay. Another one, sprint speed, 40, 80. And of course, the orientation, the plan, and on age, the same with Harshit. So let's see our tensile strength test results. You can see over there that the best results were obtained in case of PLA, I mean 51 megapascal. Yeah? I saw some research on the technical literature, 46 megapascal, 48 megapascal. Yeah? But it's up to the technical parameter that we used, yeah? And it's not compulsory to be, of course, the same value. High density PLA, around 46, impact PLA, 33, Extrudr, you can see the Extrudr group, yeah, from 28 megapascal to 32. Fiberwood, yeah, not so good, but very good surface quality. Biofila linen, yeah, and silk from 25 up to 33 megapascal. You can see now the DSC analysis. We already make the, let's say, the DSC analysis for both. I mean for PLA filament and PLA sample, yeah, for all the materials. High density PLA green filament, high density PLA sample. Impact PLA gray filament, impact PLA gray sample, yeah, to compare, yeah, the results, yeah, between the filament and the sample. So the glass transition temperature is around for all around 341, you can see, Kelvin, yeah, and behavior similar for a heating cycle, as you can see over there for both material. I mean for all material that you see over there. I mean both on the filament and both on the sample, yeah. You can see the shape more or less are the same, yeah, more or less are the same. Maybe here it's a peak, unexpected peak, okay, with around 400 peak. For the other material, the behavior, you can see it's quite similar, yeah. Also, for PLA, impact PLA gray, also the behavior, I mean, the thermal behavior of the material, filament and sample also are the same. This means, as I mentioned before, that we can reuse, let's say, the material, yeah, to the next, let's say, 3D printing. I mean to obtain again the filament, yeah, from waste and to obtain new products. And of course, you can see for Extrudr BDP Flax, yeah, it's important to see the glass transition, yeah, 64, 63. Extrudr BDP Per, Extrudr BDP Green Tech, also 116. Actually, all the results belongs to one PhD thesis. Now he is, of course, my doctor. Yeah, I have so far 10 doctors. Yeah, and in September will be the 11th one. Yeah. Okay. So you can see also XRD analysis, yeah, in case of Arboblend V2 nature reinforced Extrudr BDP. As I mentioned before, you can see, yeah, the shape of the diameter. Yeah, quite good. And the diameter 1.74 millimeters. Yeah, you can see also the diameter for Arboblend reinforced with Extrudr BDP. Yeah. DSC analysis also for Arboblend. There are Arboblend reinforced, the same, let's say, shape and glass transition temperature. And of course, you can see also the main elements. I mean carbon and oxygen, means what? Means that the material are in biodegradable class. okay, of the material, because the main component of the material are carbon and oxygen. Also, you can see in case of Arboblend reinforced with Extrudr BDP. In case of Arbofill material, yeah, the filament was not good. Yeah, you can see, as I remember well, we cannot use. Yeah, we cannot use the Arbofill for 3D printers. Yeah, the result was not okay. Maybe we'll try to find a solution to make the reinforcement, to see the base properties, to see which are the requirements for the reinforcement, and to obtain the good shape. Fiber wood, also you can see the same glass transition temperature, and XRD analysis for fiber wood material also confirms that the material has an amorph structure. And also on the right side, the carbon and oxygen are, let's say, the main elements of the material. Yeah, so means also again the biodegradation rate. You can see also the Biofila linen with amorph structure, Biofila silk, yeah, again carbon oxygen, and also the amorph structure. And DMA analysis. I explain what means DMA analysis. Yeah, we have two thermograms of an analyzed sample present similar behavior due to the chemical composition from this point of view. Biodegradable material, more or less, let's say, the same chemical composition. So the samples show a solid state transition during the heating. Why? Because the internal friction 10 delta has two maximum peaks, you can see, yeah, at the temperature of each material around 334 in case of Arboblend reinforced with Extrudr BDP, and around 2 Kelvin degree more in case of Arboblend. So while the storage modulo, you can see also for fiber wood, and 952 megapascal and 1542 megapascal in case of our materials. Of course, we can talk more about DMA diagram that you can see over there. Of course, the software show us many others information about temperature, range, peaks, and so on. Always the peaks, you know, must be attributed, yeah, to the other elements, especially on XRD, on the other test. But I think it's enough for today. DMA thermogram in case of BDP Flax, DMA thermogram in case of PLA, yeah, and in case of Biofila linear. I put some conclusion that the thermogram detect different behavior of biodegradable material during the heating and subjection of on the 3-point bending test. The first two graph presenting damping curves with two obviously peaks, yeah, you can see 1 and 2, and these peaks are associated, as I mentioned, to the different mechanical response offered by the constituents, of course, of each material. SME image on the sample surface on the breaking, let's say, area. In case of PLA, you can see that SEM image is quite good. I mean, almost deposition at 90 degrees between filaments deposition on each layer. You can see, yeah, good, let's say, layers deposition. In case of high density PLA green sample on age, this time printing, here was on plan printing, you can see on the breaking area, the outer layer of the sample is characterized by large rhomboid, yeah, you'll see over there, yeah, voids from this point of view. Their appearance indicate a rapid solidification of the extruded material due to the intense heat exchange, yeah, between layers. And the impact also PLA gray sample on age printing show us, let's say, a good structure with You can see over there the interfacial bonding. In case of extruded BDP Pearl on plan printing, and another one on BDP Flax on edge printing, and the last one, BDP Green Tech, yeah, on plan printing. Some comments, it's easy to see, yeah, which is the layer. It's easy to see the extension of the deposit filament in upper layer caused by the creative space between deposit filament, but probably also due to the slow cooling of the previous deposit filament. In case of extruded BDP Flex, the second on the right, can be observed a homogeneous surface with the deposit filament plus minus 45 infill degree. So I saw also the interesting results of hardsheet concerning the fiber, yeah, inside of the sample. Maybe it's important to use the same for biodegradable material, but I just wondering about what happened with the cohesion between layers, because you are stopped the 3D printing, yeah, the layers I think will be cool, yeah, and afterwards we try to fix, yeah, the fiber wood, and we'll start again. It's important to see which is the adhesion, yeah, between layer, and which are the solution in order to have the good adhesion between layers. Yeah. Also, I would like to carry on together, yeah, for biodegradable material. Biofila linen on edge, Biofila silk also, you can see SEM image on edge, and fiber wood also on edge printing. In case of Biofila linen damage area, yeah, you can see some damage area that, you know, appear probably more or less as a result of manipulation during the tensile test, because we didn't found, let's say, another reason why appears a little bit damage area. And fiber wood, you can see the last one, low porosity in the SEM image. Yeah, we study also the friction coefficient and wear. You can see in case of PLA, the first one, yeah. In case the B1, in case of high density PLA green, and the last one impact PLA. So of course the lowest friction coefficient is in case of PLA. Also the average wear, let's say, variation diagram, you can see in case of PLA, in case of high density PLA green, and impact PLA. We study also the wear, yeah, what happened the wear during the loading force. So you can see on the left side the image of the portion of the use area and the variation recorded in the time, that occurrence of the wear for, yeah, PLA sample, high density PLA, and impact PLA gray. Of course, you can see, yeah, over there, yeah, more or less some damages area because of the melting temperature, because, of course, of maybe others factor. The friction coefficient with test time for sample extruder, you can see on the left. I think the values are very clear, and also the image on the right side of the portion of use area in the variation recorded of the time for wear, in case of BDP Flex and in case of BDP test. Why we did the wear and the friction coefficient? Because we will see we try to replace some, let's say, plastic material using one part from our car. Friction coefficient with the test time for sample, Biofila linen, fiber wood, also Biofila linen, fiber wood, and of course portion used recorded during the wear test. As you can see over there, we started, let's say, to make an example, I mean to make an industrial application. and was developed an equipment that simulates the worm wheel assembly operation on our car. Yeah, I mean assembly that is part of the car whippers drive. Yeah, because now these wheels are made from nylon. Yeah, oof, incredible material. I don't like it, really. Yeah, and now we try to make, let's say, to change from biodegradable material. What we done? We made first the climate study, yeah, on east of Europe. Yeah, I mean very deeply inside study. I mean we count, of course, approximately, but you know, high accuracy of the approximation we try to have. Yeah, let's say how many days per year will raining, okay? How many days, let's say, during the winter time will you know, snow and you know, the whipper mechanism will working and so on. Yeah, we try also to see which is the temperature, let's say -10 up to 0, let's say 20 during the summertime and so on. Was a lot of work from this point of view. Yeah, only for this study, for the climate study. Yeah. And afterwards, yeah, we design and we create a testing equipment for worm wheel. You can see, yeah. You can ask me why appears over there 2. Yeah, we design and fabricate 2. Yeah, because our many sample to study in the temperature chamber. Yeah, with the highest temperature. Yeah, many samples, and we want, you know, to save some time from this point of view. And I put here some example. This is the nylon. Yeah, usually the material used now for this type of wheels. And this is in case of PLA. This is in case of PLA green and high density PLA green. You can see this one is the initial appearance of the worm wheel, and you can see what happened with the material, the wheel teeth. Yeah, after, let's say, 1 hour and 5 hours operating on temperature chamber, yeah, at -degree. Yeah, continue working, continue. Yeah, the simulation, including also, you know, the force, yeah, applied. So you can see what happened. Yeah, some damage. Yeah, impact PLA gray, better, high density PLA. More from this point of view, damages appears, yeah, and so on. So we study 11 materials from this point of view. So from 11 materials, I think 2 or 3 have a good results. Yeah, 2 or 3 have a good results. Had a good results from this point of view. The others completely destroyed. Yeah, not after 105 hours. Yeah, 20 hours, 25 hours. Yeah, so maybe those material will be suitable on the other, let's say, conditions, yeah, for the other countries. Less maybe raining, less another changeable climate, and so on, yeah. But for east of Europe, yeah, only 2 or 3 materials were suitable from this point of view. Yeah, we are going further from this point of view, and we'll try to make a proposal, yeah, maybe to the automotive company. We have also an automotive company in Romania. Yeah, you know, already know, together with Renault. Yeah, and we'll try to make some proposal. Also, we can use the biodegradable material for the other parts, not only, yeah, for this example. Yeah, but it's up to the producer, the price, and so on. Okay. So that's all that I wanted to mention during the 3D printing of biodegradable materials. Actually, Harshit helped me, yeah, with the introduction, with the theory from this point of view. I didn't put all the information here. Yeah, I put only the abstract, yeah, to make an idea. And of course, we can carry on together if you are interested in this, let's say, materials, biodegradable materials, and you can use on different application. You can find industrial application for sure, yeah, to replace the materials. Yeah, you have to study, you have to create a new material, because you know the material science, it's so huge. Okay, so it's like chemical research. Yeah, you know, they put over there 2 liquids or something like that and create something new. Yeah. All same material. We can choose the matrix. We can choose the reinforcement. Yeah. Of course, to know better. Yeah. What we have to do as initial requirements. Yeah. And afterwards, yeah, to obtain a good new material.
PLA is the biodegradable material. PLA.
Yeah, is the most used biodegradable material. But I don't.
What about nylon?
Nylon, it's a plastic material. It's not biodegradable material. No.
So we are adding PLA with nylon.
PLA, it's not nylon. PLA, it's not nylon. No. Two different materials.
So when we are preparing the composite, that time we are adding PLA with nylon and PLA with HD. You are shown now.
No, nylon, it's nylon, PLA, it's PLA material. I put also nylon because now the wheels, yeah, the worm wheels, yeah, are made from nylon, is my knowledge, as I know, yeah. Of course, maybe from other material. Yes, is it true? Yeah, that's why I put over there nylon as a base materials, yeah, for nowadays, for these wheels, yeah. And afterwards we put some results, yeah, that we got using PLA and others materials. Okay? Hmm? Yeah, yeah. Not matrix, no.
In your experiment, you have used the FDM.
Yes, we use the FDM. Yeah, yeah, FDM is the most used. Yeah, it's easy to use it.
If we use the injection molding.
We can use, of course, you can use the injection molding, but yes, of course, on automotive industry, the injection molding, it's of course more suitable, yeah, technology used, yeah, but you know, you have to ask the producer, yeah, if they produce the granules, yeah, from PLA, high density PLA, Biofila, and so on. I don't know now if the producer also can sell, yeah, the granules. If yes, of course, you can do it in injection molding, of course, yeah. Yes, why not, of course. We use the injection molding, but only in case of liquid wood, yeah, the first presentation for today. Yeah, could be an interesting idea, yeah, to use the, because otherwise, how can we create the to stay and to cut the filaments? That's not possible. Yeah, yeah.
Fibers, wood-based fibers. So how far will be able to get those continuous fibers?
From granules?
Continuous natural fiber, wood-based fiber. How long are those fibers? Chopped fibers is fine.
Yeah, it's fine.
Can we try to do some processing and make them continuous fiber?
Yes,
Just as in cotton we make
yeah,
threads.
I think we can try. Yeah, of course,
So
with longer
probably
fiber.
that can lead to some other activities also over and above.
Yeah, okay. Will be another topic. Yeah, another research. Yeah.
Material that you are on, and you have tested that 2 to 3 material are sustaining.
Yeah.
You have tested it for 105 hours approximately.
To test what?
To test the worm wheel
Yeah.
after 100 and something hours, 105 hours.
105 hours.
Yeah.
We tested the wheels. Yeah.
After
We check actually the right. We check the wheels. Yeah. After 105 hours,
yes.
Yeah, we check, you know, the shape, we check the teeth. Of course, the teeth, there are some dimension, yeah, to be fixed and so on, yeah. We control, yeah, after the wheels, you know, are inside of the mechanism during 105 hours, yeah. I mean simulation, exact simulation of the, you know, on our cars, yeah.
So, that might be a possibility that we are getting the result after 105 hours. It can deteriorate just after that. For if we are using it for continuous, just if we are using it for a, just as we came to the Mumbai to Surat, it is raining for 5 to 6 hours. In that particular time, because we have only simulated for 2 hours, max to max 2 hours.
Yeah, the climate, yeah, you can use the other materials that after, let's say, 20 hours, yeah, was not okay for us, okay? So you can use it, yeah? Because the climate analysis was done for 1 year, yeah? 1 year, let's say, functioning, yeah, of the mechanism, 1 year. Not only for a couple of hours. I forgot to mention, yeah? The climate analysis is for 1 year. And that's why I put over there 105 hours. Because you have to ask, yeah, of course, few hours can use the other materials, yeah? With, let's say, bad results for us, yeah? Yeah, but here it's raining, let's say, longer time compared with East of Europe, and of course, you have to change the climate condition, yeah, and for sure the number of the hours will be longer, yeah, bigger.
Sir, there is a scope of mixing those components, those recyclable or biodegradable components with the clay, with the ceramic.
I didn't try with ceramics now. To coating the plastic with ceramic and so on?
We are just like concrete 3D printing or cementitious 3D printing.
Oh, I didn't try.
There is a clay-based 3D printing or paste extrusion 3D printing, in which we can add the biodegradable material and have the sustainability.
Yeah, oh, could be, yeah, could be, yeah, yeah. Because of the accent, I have to put down here. Yeah. From time it's difficult for me, the accent, really.
Sir, can you see use of PLA in biomedical field as an implant or?
I think so, possible, but maybe coated. But
No,
maybe
but
coated
in that
also.
Case, in that case, there would be many government regulations.
Yeah.
Regulations.
It's biodegradable material. Oh, so and so. Maybe coated with ceramic nanoparticles. I think coated. I think.
But
I don't know.
There are more restrictions. Nowadays, there is more awareness. So
Because there are a lot of condition, yeah, on the implants, on the interface.
Yes.
Yeah, it's very, very, difficult to have an answer
And the other
for
thing
all
with
the
PLA is
requirements.
that the PLA, with time, because it is biodegradable, it can redegrade. And with time, it becomes slightly, its properties reduced. So if you are putting it in body, and if it loses strength, and if it breaks, then it's more difficult. So
Yeah.
I was thinking
It's
in a way
inside of the medicine, there are, compulsory conditions.
by implanting steel or titanium,
Yeah,
after some time we have
mostly it's used titanium.
yeah. So
What I see that most of the engineering field students or engineering teachers are not directly collaborating with the doctor.